Okay, we're in section number 10, and we're doing something that was actually covered in Math 119, which is the intermediate value theorem. And we'll certainly go through that one step at a time. All right. After we go through the short lecture material, we will go through examples. All right. As we go through the examples, hopefully what's been covered in lecture becomes more familiar to you. All right. The intent, though, is at some point you get busy with study and trying. All right. So let's go back to the lecture. I'll go to the whiteboard, and it'll be short. Not much to say about this. It's just to review what you've done in Math 119. And again, we're looking for you to read and then kind of try to understand what you've read. But let's take a look. So we got this guy, Karl Weierstrass, German mathematician. He proved the intermediate value theorem. It wasn't easy to do, by the way. Some said that he proved the obvious, but however, he proved it. All right, he did prove it. All right. Now, this was done in Math 119 as well. And you used it in 119 to show that there was an existence of a root, which I'm going to say is probably the most common use of the intermediate value theorem, is to show that there's an existence of a root. What's a root? A root is where a function takes on a zero. So I'm going to say that for the most part, I'm going to continue with that root finding, root existence, not finding, but root existence skill. And let's just read this to you. All right. So it says, suppose f is continuous on a closed interval, and w is any number between fa and fb, where fa does not equal fb. We'll visualize this in a second, by the way. Then it says there's a number c on the open interval between a and b, for which fc equals w. Now, a lot of people read that, have no idea what they've read. All right, so what I'm going to claim over here is, what they're telling me is, they say, suppose f is continuous on a closed interval. So I'm just going to, draw a picture of a function that looks continuous on a closed interval between a and b. So I'm going to say this over here is a, f of a. Again, I'm just reading and trying to understand visually is what they said. And someone says, is that the function you're talking about? No, I'm just saying I got an example of a function that's continuous on a closed interval between a and b. Now, what else did they say? They say there's a number between fa and f of b. Well, I'm going to put that down now. So there's a number, w, that's between fa and fb. So what does that mean? There's a number between fa and fb. Well, I'm going to put it right over here. That's the w now. All right, there's a number between that. There's a number between fa and fb. Okay, what do they go on to say? fa does not equal fb. Well, I kind of clearly see that over there. Fa and fb are not equal. Then they said there's a number c between a and b. So I'm going to point that out to you. They say there's a number between a and b, and they say there's a number c between those two. So c's over here somewhere. All right. Now, what do they say? F of c equals w. Well, what I notice right away, I see one here, and I see one here. So what am I saying over here? F of c is equal to w. So I'm going to say this one over here might be C1. This one over here might be C2. All they say, there is some C. They don't tell you what it is. There is some C. All right. That's all they're telling you. All right. Let's take a look at an example. And it says, let's suppose you're asked to show that has a zero. So really what the question over here is, that this is like a 119 question. They're asking you to show that there's a zero to the problem on that interval. So let's write this down. So f of some number, I have no idea what that number is, would equal zero. So you may remember Math 119, this was rather a difficult issue for you to find those roots, but they want me to find it. So I'm going to tell you that this over here is probably the most typical W to use. And what's that W going to be? W is equal to zero. It's a root existence thing. So what do I got over there? It's polynomial. Polynomials are continuous everywhere. So if they're continuous everywhere, they're certainly continuous on a closed interval. This needs to be stated, by the way. So you need to state that. Give me 1 second. You need to state this. Let me go back. You need to state this. and we're using the IVT. You need to state that. The next thing you need to do, right, is evaluate f of minus 2 and f of minus 1 to make sure they're different. So f of minus 2, I'll go through this in a second, is equal to that number, and f of minus 1 is equal to this number. Let me go through that with you. So I'm going to do the endpoints. F of minus 2, what's that going to be? Well, it's going to be minus 8 plus 8 minus 2, which is minus 2. Well, that was convincing. F of minus 1 is equal to minus 1 plus 4 minus 2. And I would give you 1. All right. We just verified this over here. Again, what's our W? Our W was a number between f of A and f of B. I hope you can agree that 0 is between minus 2 and 1. So what they do now, they say that the IVT applies now. All right. So by the IVT, there exists a number C. They don't tell you what it is, by the way. On the open interval between those endpoints, minus 2 and 1, there will be a C on that open interval where I'm going to get that 0. All right. We're illustrating the obvious in the picture, by the way. What do I mean by that? If you look at this picture over here, it's a graph. This is the graph of the function. It's cubic, by the way. And the beginning of it was, I'll just write this down for you. It was minus 2, comma, minus 2. This one over here is going to be, what was that? It was minus 1, 1, right? Yeah. And what am I saying over there? What's the W? The W is equal to 0. What's that? It looks like this over here. And this is where the C would be. All right. What's the C going to be? Well, you can blow this up. It's like minus 1 point something. I don't know exactly what it is, but it can be done. We can figure out that root. It might be difficult, but we could figure the root out. All right. So let's go to the next page. We're done with that. And we're at the example. All right. Now, I want to point out, if you're reading these things, which we do recommend you do read, not to memorize, but to have an appreciation of what's being presented to you. It says what's not obvious is the value of C, but you can take a pretty good guess at it, which we did talk about. It's like minus 1 point something. Look at the picture, by the way. But you can use software to get a good approximation and possibly the exact answer. There's a footnote over there. We'd like you to take a look at it. And it says on my calculator, and on my calculator, it returned this number. Whoops, sorry about that. My calculator, and I mean that, I actually used the calculator to do that. I got this number, all right? Mathematica was able to compute 3 real roots to the problem as expected, all right? It was expected to do that. All right, let's take a look. And what I'm going to do now is say we're done with the lecture part. And I wanted to claim what the lecture is. It's a review of what you did in Math 119, right? The only difference now is you have a more formal approach to continuity, all right? 119 was much more, imprecise, but now you know the definition of continuity. We've done a whole section on continuity. All right, so I'm going to say lecture's over, and we need to get busy. Certainly, next time we come back, we'll be on the examples. Okay, thank you.